Good day, grade 8. Our topic for today is part 2 of the axiomatic system. Let's have the first axiom, which is transitive axiom. If A is equal to B and B is equal to C, then A is equal to C. Let's have an example. If A plus 4 is B and B plus 4 is equal to A, then A is equal to B. That's an example of transitive axiom. Another one, if A is greater than B and B is greater than C, then A is greater than C. Let's check. So let A be equal to 5 and B is equal to 2 and C is equal to A. So we have 5 is greater than 2, yes, and 2 is greater than 1, right? Then 5 is greater than 1. So this is an example of transitive axiom. Next, let's have the addition axiom. The rule here is if A is equal to B, then A plus C is equal to B plus C, wherein A and B has the same value. Like for example, let A and B is equal to 2. Then C, of course, it has same value since it's the same letter. So let C is equal to 5. Substitute the value of A, B, and C. So we have A is equal to 2 and B is equal to 2. Let's just prove the axiom is right. Then A, wherein the value of A is 2, plus C, wherein C, where the value of C is 5, is equal to B. The value of B is 2, and the value of C is 5. So if 2 is equal to 2, then 2 plus 2 is 7, and 2 plus 5, I mean 2 plus 5 is 7, and 2 plus 5 is equal to 7. Therefore, the axiom is correct. Another one. If A is greater than B, then A plus C is greater than B plus C. So let A is equal to 5 and let B is equal to 4 and let C is equal to 3. So substitute the value. If 5 is greater than 4, yes, then 5 plus 3 is greater than 4 plus 3. Let's check if the axiom is correct. So if 5 is greater than 4, then 5 plus 3 is 8. Yes, then 4 plus 3 is 7. So the axiom is correct since 8 is greater than 7. Next axiom, we have multiplication axiom. So the rule here is if A is equal to B, then AC is equal to BC. So let A and B is equal to 2, since A and B is equal. Then let C is equal to 5. So if 2 is equal to 2, just substitute the value of A and B to the axiom. So A is equal to 2, B is equal to 2, then AC, so 2 times 5, and BC is also 2 times 5. So if 2 is equal to 2, then 2 times 5 is 10, is equal to 10 also. Therefore, the multiplication axiom is correct. Next example, if A is greater than B and C is greater than 0, then AC is greater than BC. So let's have an example. Let A is equal to 5, let B is equal to 4, and let C is equal to 3. These are the given. Next, substitute the value of A, B, and C to the axiom. So we have if 5 is greater than 4 and 3 is greater than 0, then 5 times 3 is greater than 4 times 3. Okay, if 5 is greater than 4, yes, 5 is greater than 4. And 3 is greater than 0, yes, 3 is greater than 0. Then 5 times 3 is 15. 15 is greater than 12, yes, 15 is greater than 12. Therefore, this axiom is also true. Next, let's have the existence of additive inverse. For every real number a, there exists a real number negative a such that a plus negative a is equal to negative a plus a, which is equal to 0. When we say additive inverse, these are the negative numbers. Like for example, the additive inverse of positive 5 is negative 5. Then the additive inverse of negative 5 is positive 5. So like for example, we have positive 1. Then the additive inverse of positive 1 is negative 1. So 1 plus negative 1 is equal to negative 1 plus 1, which is equal to 0. Next, 2 or positive 2. The additive inverse of positive 2 is negative 2. So 2 plus negative 2 is equal to negative 2 plus 2, which is equal to 0. In additive inverse, we always get an answer which is equal to 0. So next, let's have the existence of multiplicative inverse. For every non-zero real number a, there exists a real number negative a such that a multiplied by 1 over a is equal to 1. So here we have multiplicative inverse or diffraction of a whole number. Like for example, we have positive 2. The multiplicative inverse of positive 2 is 1/2. Then like for example, we have 9. The multiplicative inverse of positive 9 is 1 over 9. So example, we have 2. Then the multiplicative inverse of positive 2, we have 1/2. So 2 multiplied by 1, we have 2. Then copy the numerator, which is 2. Then 2 divided by 2 is equal to 1. Therefore, multiplicative inverse or existence of multiplicative inverse is true. Let's have another example, which is 4. Then the multiplicative inverse of 4 is 1/4. So 4 times 1, we have 4. 4 times 1, we have 4. Then copy the numerator. The denominator. So we have 4 divided by 4, we have 1. So next, let's have the existence of additive identity. For every real number a plus, wherein a plus 0 is equal to a. So if we add any number to 0, we get the answer, which is identity or the number itself. So like for example, 5 plus 0 is 5. So identity of 5 is 5. Then 8 plus 0 is also equal to 8. These are example of existence of additive identity. Next, existence of multiplicative identity. So, how do we get the number itself? By multiplying n number. So, for every real number a, we have a times 1. So, we multiply it by 1 to get the answer or the number itself. A multiplied by 1 is equal to 1 multiplied by a is equal to a. So like for example, 5 times 1 is 5 and 1 times 5 is 5. So we get the number itself, which is 5. Next, 21 multiplied by 1 is equal to 1 times 21 is equal to 21. These are examples of existence of multiplicative identity. Next example, we have trichotomy axiom. For every real number, A and B, exactly one of the following is true. Maybe A is equal to B, or A is greater than B, or A is less than B. Again, in this axiom, exactly one of the following is true. Either A is equal to B, or A is greater than B, or A is less than B. And that's it. Thank you for listening. Let's call it a day. Goodbye, grade 8.